Today we're going to talk about integrating deep learning into ArcGIS workflows. So we're not going to talk about the tools. There's been a couple other presentations prior to this about how to use some of the tools like export training data for deep learning. We had a hands-on technical workshop yesterday, and there's been several other demonstrations of that. Today what we're going to talk about is some of the work that the AI and machine learning team within Esri has been doing to tackle specific use cases by applying deep learning to real-world problems. So what you're going to see is work that we've been doing for actual customers, and we're going to try to give you a pretty good variety. Most of the deep learning work that we've been doing is in the field of computer vision, so we're trying to detect objects, classify things, and we're going to go into good detail about that. So I'm Daniel Wilson. I'm the technical lead for the team. I'm joined by Shiraz Sohail and Amin Tayebi. They're data scientists on the AI and machine learning cross-sector team. And they've done some pretty terrific work on the projects that they're going to show. Before we get into that, I just want to clarify in case there's any confusion about when we say AI, machine learning, and deep learning. Artificial intelligence is a very broad field that covers many different disciplines, not just machine learning, but also other approaches. It really has its roots back in the 1950s, actually probably the 1940s and 50s when the term was coined. And it has evolved pretty dramatically since then. So artificial intelligence started out as basically defining rules and ways of acting to make decisions, and then it slowly evolved to more data-driven approaches. Machine learning starting out shortly thereafter, neural nets being invented in the 50s and 60s, and then seeing initial failures, and then a resurgence in the 80s, followed by more failures because we didn't have the hardware or data to really utilize them effectively. Back in, I believe it was 2012, a very prominent image classification competition, the ImageNet competition, was won by a deep convolutional neural network, and that's one of the things that really spawned this whole deep learning revolution that you've been hearing about for the past several years. I think it's reached the point today where it can really be applied to real-world problems, and that's why we're putting a very large focus on deep learning capabilities within ArcGIS, because it can accelerate so many different workflows. When we talk about machine learning, traditionally when people say machine learning and not deep learning, they're referring to classical algorithms that basically learn from data that has been hand curated. So this is typically not things like images. What we're doing is we're choosing features that represent the data we're looking at. And that could be images as well, but the example that I'm going to give here is classifying fruit based on their texture and their weight. If you have parameters about your data, and this could be fields within a feature class, or it could be information like this, machine learning algorithms would take this information and try to figure out what the best label to assign to these fruits based on this input. That's an example of supervised learning, where you have input data and you have a target label. Supervised learning can be used for classification, which would be determining between different types of fruit, or regression, which would be predicting some continuous number. There's also a couple fields of machine learning, unsupervised learning and reinforcement learning, which are both very important, but we're not going to talk about today. Unsupervised learning is used for finding structure, finding anomalies, finding patterns within data, but not necessarily going directly to labels like supervised learning is. And within ArcGIS, we have tools to do some unsupervised learning, such as the density-based clustering and the other clustering algorithms, and the space-time pattern mining. Those are examples of unsupervised learning because we're not explicitly programming them with labels to find. Reinforcement learning is a really interesting area. We're actually doing some research in it, but we're not going to talk about that today. Reinforcement learning is the type of machine learning where you have some sort of agent acting in an environment by taking actions. And then the agent learns by receiving reward and improves actions based on that reward. And it's done some pretty extraordinary things to date, but it's still unclear what the future of it is in terms of real-world applications. And we'll start to see more of that come out in the next several years, I think. So deep learning is a subfield of machine learning. And really the difference between machine learning and deep learning is the feature engineering for machine learning is typically done by hand, either by heuristics or by expert human knowledge to craft a set of features that are going to be used by the algorithm. The power of deep learning is that feature extraction and the classification is performed by one end-to-end system. And usually we refer to those as deep neural networks. There's other algorithms that fall under the umbrella of deep learning, but when someone says deep learning, more often than not, they're talking about deep neural networks, specifically convolutional neural networks, which is the algorithm that was used to win ImageNet back in 2012, and advances have come so far since then, and the accuracy is reaching human levels in a lot of areas, and it can process data way faster than humans can possibly process it. So the topic of today is integration. So we're not talking about these algorithms specifically. We're not talking just about the tools, but we're talking about applying this to real world use cases using the ArcGIS platform. So the product teams have put a lot of care into making ArcGIS an open platform. It's not, it doesn't contain all of these deep learning tools within the platform, but it's really easy to integrate with them externally. So that way you can put all of the logic in something like TensorFlow, for example, which Google has put a lot of care into building as a world-class deep learning framework. And we can leverage all of that within the ArcGIS platform. We can also leverage machine learning services such as those from IBM Watson, Microsoft Azure, AWS. And then we can integrate with normal machine learning frameworks as well. Scikit-learn is a very popular machine learning library that's used. Today we're going to talk about integration with the Keras deep learning framework. Yours is Keras? Yeah, actually, it's going to be all Keras today. So Keras and some TensorFlow. So we're going to talk about integration with those frameworks and various aspects of the platform, including GeoEvent and Pro and several other tools. Yeah. So I'm going to go ahead and hand it off to Shiraz. He's going to talk to you about an application to disaster response using deep learning.
All right, thank you guys for coming. So this is some work I started tackling about 3 months ago. It's something that was kind of really meaningful to me, and it's really kind of an important problem in general. It's basically looking at what happens after a disaster and how we can use AI to optimize the response. So I'm going to start off by just talking about kind of like the major disaster we focused on, just the general workflow we built out. I'm going to show some code. I'm going to show some of the ArcGIS tools I used, not only to actually help develop the model, but also visualize and get actual intel to people on the ground to be able to help with the response. So a lot of the data for this model comes from Hurricane Michael. So Hurricane Michael made landfall at 12:15 CDT, October 10th, 2018. So it touched down at Tyndall Air Force Base in Mexico Beach, Florida. That base was almost completely leveled. They had wind measurements around between 86 and 139 miles an hour. The nearby town of Mexico Beach was also almost completely leveled. There were parts of houses all over blocking the streets, and some of the trees that were not flattened actually had the bark ripped right off the trunk. They had storm surges, large storm surges throughout the area, and then the storm kind of moved through Panama City. And there was billions of dollars of damage in Panama City, and one of the largest psychiatric hospitals in Florida that was there was completely blocked off by debris. They actually had to send a helicopter with supplies to that hospital. Towards the end of it, in Panama City, there were about 14-foot storm surges. And after 9 days total, and basically by that time that storm passed all the way to Georgia, there were 72 confirmed fatalities and $25.1 billion in damage. So really the key thing here is that how does a government agency, how does someone like Red Cross or FEMA respond to this disaster? Well, the first thing is to be able to find the people that are most affected by the disasters. So a lot of that involves aerial imagery, but once that imagery is collected, people are basically, they have analysts that are looking through this imagery and looking for damaged structures. And the problem with that is, first of all, it's extremely labor intensive, especially in post-disaster where time is a huge commodity. But also you can miss a lot of people that really need help. So imagine, you're somewhere in Bay Head, Florida, right? Small town, kind of has a little creek surrounding it, maybe, 1,500 residents or so, and you're in one of the houses that wasn't built up to code near the creek, and you're trapped in there, and someone is sitting there looking through imagery at FEMA, and they're looking at something like Panama City where an entire neighborhood has been leveled. And it's really, if you look through the imagery, there's a lot of houses where they're easy to miss. And maybe not even miss, some of them are just difficult to get to and they present a huge routing challenge, which I'll talk about. So that's kind of the motivation behind this work, is to be able to use AI to help identify damaged structures that might contain, people who need rescue, people who are still trapped, people who need immediate assistance. So this is the image from the Tyndall Air Force Base where the hurricane touched down. So the kind of general workflow we're building here is basically, like I talked about, we want the AI models to detect damaged structures first and foremost. But once we started being able to do that, we thought about, okay, how can we turn this into action on the ground? So one of the key problems with actually, once you have damaged structures, one of the key problems is actually getting to them. So I was talking about the psychiatric hospital that was completely blocked off. There's several structures like that where even routing to them is a huge challenge because of damaged roads. Some roads, especially around Panama City, just completely washed away. But some roads have debris. Some roads are somewhat passable, but you need either special equipment, you need a winch or something to pull debris so they can send first responders. And so that was kind of our second area of focus. Once we can detect damaged structures, we now need to detect damaged roads. Once we have a model for doing damaged roads and damaged structures, now we can put that together by actually having a routable network. So now we're strictly in ArcGIS territory. We're building what's an optimal route given these blockages to these locations, starting off at something like a fire station where there might be first responders located. And then the last part of this puzzle is basically allocating resources and monitors. I won't talk about that too much, but basically we have all of this integrated right now with something like Workforce. So you can actually have first responders, once this model runs, getting an actual map on their Workforce app. This is my route, these are the damaged structures I need to attend to, and once I've attended to a damaged structure and I've seen if anybody needs rescue or anything like that, I can mark that off on the app and update. And that way, the comm center has all the information about where their first responders are if they need backup, but also the first responders have immediate intel about where they need to go. And there's not this rush to just get everybody to the same place and miss certain other areas. So this is kind of a theme you'll see with a lot of our AI work. It's basically getting everyone to work together seamlessly. So it's not just for this this damage effort. It's for the work that Daniel and Amin are doing and the rest of our team are doing. It's basically AI models are useless if they are just large libraries of code that one or two people in your company can run or understand. What you really need is that the output from those models be consumed, not only by analysts, but like I said, people on the ground, so they can make use of it right away. So these are kind of some of some of the roles analysts might be, accessing imagery, fixing data, preparing training data, formulating the questions, consuming a model for analysis. I'll talk about this a little bit. And then the end user. So in the damage structure case, the end users are the first responders. It's different for a lot of our projects, but what's important is being able to get it there in a way that's not, convoluted or slow or anything like that. All right, so now I'm going to actually show you guys some damage structures. These are actually from Hurricane Michael. And those are just some of the model predictions overlaid on top. So bear with me, I'm a little bit colorblind, but the blue houses are damaged as identified by the model, and the green ones are undamaged as identified by the model. So that's the first piece. I'll show a little bit of the code for this. This is the second piece. So this is the damaged roads. So here, this is basically showing two different kinds of roads. One is blocked by debris and one is passable. So the yellow is the passable. And then other colors show different categories, either partially blocked by debris, fully blocked by debris, or basically a third class or damaged road layer. So that's when the road itself gets washed away. So that the first image is the actual imagery. The second image is the label that the actual human label for that area. And then the third one is the model prediction. So you can kind of see how close they are. This is a specific type of neural network model architecture, UNet, that is really good at identifying these kind of boundaries. So yeah, this is just, pretty much what I talked about earlier. The whole pipeline that we want to kind of attack with all of our work is, get access to imagery or any other kind of, data that you have, prep it for consumption by a model for training. Part of that is obviously data labeling. So in this case, I actually went and labeled damage structures, which by hand, several hundred of them. I'll show you guys that too. So once you have labeled training data, which in this case was polygons on top of the imagery for damaged structures and then later damaged road segments, you can train a model and then deploy the model to production. So we're kind of exploring different ways of doing that. Right now, some of the paradigms we're exploring is basically having it deploy straight through Pro using a tool called Detect Objects using deep learning or classify pixels. We're exploring uploading these to Portal as a deep learning package so it can be easily disseminated. We're exploring putting them in notebooks, sharing those notebooks so data scientists and other developers within the company can actually look at what the underlying architecture is. So once you found one of those avenues for consuming a model, you can run inference at scale. So I won't talk about that too much, but a lot of the tools I mentioned can basically parallelize these tasks. So if you're doing this kind of damage structure detection over a large area, what it'll do is it'll basically chunk it up into little tiles, and it'll basically feed those tiles in parallel to the model, so that it's not going area by area by area. It's processing all of those at the same time. So it runs quickly, and that's important for use cases like this. And then there's a feedback loop. So this is something I really like about the whole ArcGIS infrastructure is that if I go to a damaged structure, I'm a first responder, I'm consuming this model output, and I go to a damaged structure, and I'm like, that's not really damaged, right? I can see why it might have, maybe it's flooded or something, but there's no visible signs of damage. So I can go into my Workforce app and I can mark, okay, this was incorrectly classified, and then that is fed back into the ecosystem so the model can consume it. So a lot of these models, they have the capability to get better with time, especially from actual, responses on their predictions from people who are utilizing them. And the last part of it is obviously taking action. So this is going to be the last slide in the deck, and then I'll just go and show some hands-on stuff. So this current planned extensions of this model. So right now we're actually showing just bounding boxes around damaged structures. So you guys saw that earlier. We actually have the capability now to do just footprints. So actually just creating those blue boxes would actually only encompass the roof of the structure. So you get a better idea of how the structure itself is laid out. So maybe you want to look at, entrances, exits, and have better planning around that. We're also looking into adding damage level and types. So that's important for actual damage assessment from like insurance companies. Is this a fully leveled structure? Is there small, are shingles pulled off the roof? Is part of the roof caved in? And also we're kind of looking into support for flooding and fire, other kinds of disasters. Distributed raster analytics, that's kind of already working. And adding additional imagery types, orthogonal, drive-by imagery. That's really more for like insurance assessments. They all actually, once the disaster has subsided and people have been rescued, like they'll actually send vehicles out to photograph these structures, assess the level of damage. So we're trying to get it to work with that too. All right, now I'm going to show some stuff in Pro first. So this is, I was mentioning earlier that I went in and actually labeled damaged structures. So this is what that would look like. So it's basically, you can go into, maybe I should show it. So you can go into edit, like if you have an underlying imagery layer. So this is the imagery layer from Hurricane Michael. Once you have an imagery layer like that, you can actually go in, you can click create on the edit tab, and then you can actually go in and draw, polygons or squares. So I can say, maybe this looks like a damaged structure. Part of the roof is caved in. So I can go in and I can actually just create a little rectangle around it. And after I'm done labeling all the damaged and undamaged structures, there's a tool called Export Training Data for Deep Learning. I'm not actually going to run it because it might take some time, but what it lets you do is it lets you take an imagery layer and a feature layer, which is basically all these labels that I created. It lets you take that and basically output little image chips. So the way a lot of these deep learning models are trained is they'll basically consume an image chip, and they'll consume a file that tells you where in the image chip the feature is actually placed. So for these, you might have an image chip that has one or two houses contained within it, and then the text file will tell you this is the coordinates of the square or polygon or whatever that contains the feature. And then it'll look at the model will consume a bunch of these chips and a bunch of these labels, and basically train itself to understand, okay, this combination of pixels is usually indicative of a damaged house. Or, pixels laid out like this, might indicate a damaged road. And so the model is, ideally if you have good examples and a good variety of examples, it's generalizable to other similar situations. So once you run that tool, you'll get some output that looks like this. And this is actually just kind of humbling to look through too, because you can see the level of damage on some of these structures. And it's not just houses, it's factories, larger, commercial retailers, parking lots, different kinds of things. So I'm not going to show too much of the code because it's usually hard to read, but I'll pull it up and I'll show you how it's working. So there's two parts to this model. The first part is basically detecting whether there's a building present or not in the image. And then the second part of it is classifying the building itself. So the first part of there's actually two different models working in parallel here. The first model will take an image like this and it'll identify structures that might be buildings in the image. So here I'm pulling up the first mask that's detected by the model. So the first model is a mask RCNN model for those who are familiar with it. And it'll basically say, okay, I see a building in that part of the image. And then once this first model spots what might be considered a building or an outline of one, it'll go in and it'll crop that chunk of the image. So it'll crop it and it'll split it into another image, and that image will be fed into a second model, and that model will basically just spit out a label. So it'll say, okay, that's a damaged structure, that's an undamaged structure. So that's kind of that's really the gist of it. This is kind of it working across. This is just some of the. So this is the function that'll do all of it. And once you get that running, I'll show that later. What you'll get in Pro is, so here I actually outputted a raster. You can output actual polygons like you labeled, but the raster is a little bit better to look at, I think. So we zoom to layer. So it'll output something like that. And basically you can run all this within Pro and you'll get something like this out that you can upload to ArcGIS online, or if you're an analyst, you can use it directly from within Pro. And this is basically it's telling you, and this is for an area that the model has never seen. So these are not image chips I fed in and the model memorized them. This is over a completely new area. And it's saying these blue ones are the ones I think are damaged structures. So you can look at some of these. So that's the first part of the workflow. Once you get to that, we were thinking about roads. So the road section presented actually kind of an interesting problem. So it was not something we initially planned, but for a client that was coming, this was kind of a critical part of the workflow, and we had to get it done much quicker than we thought. So we were like, okay, for roads, the big problem is we need labels. Like, it took me, almost a month to label all those damaged structures. There's well over, 3,000 of them now. It took me almost a month to do that, alongside my other work. So we had to basically have a team that we had to put these labels out within a day, basically, several hundred roads. So we marked an area of interest. We're like, okay, we think, this area, if we mark all the roads in this area, that should be enough to train it to have decent model. Problem is that area had almost 1,500 roads in it. And what we did was we actually created a ArcGIS online app that we sent out to a bunch of people on our team, a bunch of people on different teams, and we're like, look, all we need you to do is we need you to look at this imagery, click on a road, and label it as damaged or blocked by debris, damaged, partially blocked by debris. That's it. And the way we kind of incentivized people to do that was we actually created an app that tracked progress. That's all. This took the better part of half an hour for one of the guys on our team to whip up. And you can see, like, these are all the people that we're labeling, and it kind of tells you how many are categorized, how many are uncategorized, and it tells you the distribution. So about 23% of the roads in this area are completely blocked due to debris. 20% are only partially blocked, and about 12% of them are destroyed. So it's actually interesting, because I was labeling this, and around 4 p.m. I left, and I was like, okay, I'm top on the leaderboard, and then next day I come in and I'm like last place. So it's cool. I mean, it's an interesting way to kind of incentivize people to do something really quickly. And this was initially, it started off because we had a tight deadline, but really this is when you have a serious disaster, everything is tight deadlines, right? Like, every minute counts. So if you can just create a web app within an hour and send it to a bunch of people to just label and kind of crowdsource that effort, even better. So the cool thing is we got this whole area done basically within the day. And we were able to actually have a model consume it and do the predictions on top of it. And once you did those predictions, which I showed earlier from that UNet model, that was actually based on only this chunk of training data. Once you have the model consume it, Now we can put together that entire workflow. So these are the roads that are either impassable due to debris or damaged. And once we have that, we can look at damaged structures in an area. So these red ones are the structures that the model has classified as damaged. Once you do that, we can designate an area where first responders might be deployed from. So in our case, it's the fire station down here. So now you guys can probably fill in the blanks. We have the damaged roads, impassable roads. We have the damaged structures. The next piece of this is routing. So this is something, Esri has done for years and years and years. It's really good at. So it's really easy to do through network analysts. You can basically put in blockages. You can put in locations you want to stop at. You can put in how many, first responders are being sent out. And kind of based on that, not only do we get a route, we also can get basically the order that these houses should be stopped at. So you can see sequence numbers associated with these. All right, so that's kind of most of what I had. That's how we kind of attacked this problem and took it from end to end. Basically, not just creating an AI model to detect something or put labels on stuff, but getting all the way to sending intel out to people on the ground and being able to get people out in disaster scenarios. So, thank you.
Can you guys hear me? Is it good enough? So and my background is environment, and I'm actually interested to apply AI and machine learning in environment space, basically like land cover, water quality, ecosystem services, and climate change. And that's how I actually started with the first project in GeoAI team. So I'm actually going to walk you guys through two kind of end-to-end solution that we have currently. The first one is for land cover classification using deep learning, and which kind of integrated, in ArcGIS API and Python and Pro and Keras basically. And second one is GeoAI. That's basically our new solution that we kind of kicked it off basically last week, that I'm going to show how we integrated TensorFlow, GeoEvent, and AWS. So land cover, it has been around probably since human exist. It was basically very important for human to change the land around and see what's the consequences, based on like population growth, how urbanization happened, and other stuff. So we had a customer that they were interested to do and ask us to kind of create high resolution land cover map using nape imagery, which is kind of 1 meter resolution with 4 bands. And the idea that was behind this, they had actually working with farmers, that when they check, the report that they get farmers actually had inconsistency with what they could actually see from imagery. And it's a basic kind of fraud detection, but the base is going to be basically land cover classification. So I'm going to basically walk you through the whole process and show that how easy it is to integrate Python API, deep learning with Pro, and how you can do everything here. So the story was simple. We had these nape imagery that we want to classify those, something lower that you guys can see. The classics that kind of they asked us to do was building, roads, water, harvested area, forest, and planted. And we use Pro, Python API, and deep learning, and also virtual machine to kind of train the model. So the data sources that we had, was kind of our state of Alabama. We had basically 12 tiles. We had 8 tiles on the top of Alabama, and we also had another 4 lower down. So, one of the good way to process this in Pro without crashing is actually converting to mosaic dataset, which is gonna mosaic those nape imagery, create footprint, as well as the boundary of a study area that you have. And after that, you can start to add your nape imagery to your mosaic dataset, which, this is a final that you guys can see over here. And we also have labels that normally, because this is a supervised approach, we need labels that basically shows where are those land cover classes located. So the original label that we got was actually in vector format. I just color code based on the classes that they were, like forest, planted, harvested, or building area. And in order to feed it to the model that we had to kind of convert it to raster and fill those areas that were kind of no data with 0. Basically those purple area that you guys can see. From there, we had our mosaic data set on the top. Then we have our label that converted to raster. Then we feed it to export deep learning training tool in Pro. What basically does is just based on the chip size that you define, it's going to break down those imagery to the smaller piece. That's where from there you can go to train your model. So the idea, land cover classification is not actually new. This has been around for at least 6 years, before, after that Landsat actually launched, we started to get imagery or for entire planet. This is kind of basically showing that how different land cover classes actually respond, based on the reflectance. And that's one of the, this signature is basically like footprint that, is kind of distinguished between different classes. And what model does is actually looking at this different spectrum and using convolution neural net to identify or separate these classes from each other. So the model that we used was called UNIT. So it's obvious what's called UNIT, because it has a U shape. So the original UNIT that we had was kind of close to 33 million parameters. And based on the data that we had, we couldn't basically train on that because we didn't have enough data set to train the model. So the way that we solved it, we just make the network actually smaller. We can kind of reconfigure the model, remove some layers that we had, and kind of remove also made the filters that kind of identify features smaller. And from there we could train the model. So from what you see, the left side of UNIT is actually doing downsampling. Basically it goes, from larger image to the smaller and smaller to identify those features. Then from, right side, it start to upsample, actually bring it back to the original size that you had. Here, the chip size that I used was 128 by 128, again, because I didn't have that much data set. And plus, we have that skip connection, actually bring your left to the right side and add them together. And what this does is actually adding original context. Because when you do downsampling, you are going to lose your info, And very similar to the resampling, actually. And what this does actually help you to bring back those contexts together, plus your features. And so again, the input, is going to be the imagery that we get from export training deep learning, and your output is going to be those labels. And what's happened, you basically feed it to the model. Model is going to go through different iteration, adjust the weight and bias, and calculate the model that you can use. So after building the model, so we actually kind of do the inference on the model. So basically, if you have new area that you want to use your model, so you don't need actually to label them again. So you can actually classify pixel using deep learning in Pro. And it's super simple. You just input your raster that you have, which can be nape imagery for any area, or any other imagery that have formats, RGB plus near infrared, and you can consume it here. Then on output side, you just define the name of output raster you want, and we pass you the EMD file plus the model that basically you can incorporate it here. That EMD file is a JSON file that contains a path to basically your model, define chip size and define how many bands your model should use from the imagery to make prediction for land cover classification. We then calculated, accuracy, precision, recall, and overall accuracy was one of the common one that used in machine learning area for see how the model perform. And we compared it with the baseline that we have. Our baseline basically is 75% using conventional machine learning approaches. So with this one, we could get close to 90%. For some of the classes that we had more sample, it was over 90%. For the others, like building or water, that they were less sample, they were kind of between 85 to 90%. So then from here, I'm going to show you some samples. Basically, this is the original nape imagery that we have. And this is a classified one. So it seems that it did pretty well, One of the things actually shocked me is about finding swimming pool in the backyard. Basically, if you go in your backyard and you try to get in pool, we can basically see you from here. So this is kind of amazing, right? I didn't, to be honest, expect to see those pools or those small area around. It detects basically every single building. It doesn't miss anything, even that they located inside the forest without like forest cover. So here are some, like misclassified area. I guess it didn't classify well. You can see, I guess this one is the correct one. It's the swimming pool that I was mentioning. And these are those shadow that kind of, forest actually fall on the road. It's basically called shadow. So it seems that because we didn't have enough sample from shadow, it couldn't actually kind of classify them. If the shadow is too, they weigh too much, it has problem, but rather than that, it's just do pretty well. Then here is the second example. Basically, it doesn't miss any building or forest, basically. It just detects everything. For forest, easy, but still it has some area around here. You can see the shadow, but here that we don't have shadow, it's perfectly fine. Then, when you build a model, you have to see the both sides, right? Good side and bad side, and there is no perfect model, so. And here I think is the last one that you can see. This is all the buildings. Here are the planted area and harvested area, and here is the forest. And we actually have a GeoAI block that we actually put everything out there, that if you guys are interested, you guys can go there and read more about there. And I actually linked it to GitHub that contain all the code and everything that you guys can go and try it out for your own study area. I'm currently working with Portugal and Germany and another country that I don't remember to replicate this process for them for UC. So next one is GeoAI. That's kind of interesting solution that we built using Python API, TensorFlow, GeoEvent, and AWS. So the idea of GeoAI was kind of tracking people at intersection. So we actually had access to live feed camera from DC. And there are like 111 cameras that we get a live feed from there. And what they ask us to do is kind of get like activity at different intersection, like how many cars are passing in each intersection. These are kind of very important for traffic management to see, that what they can do to kind of make it easier for people to commute in that location. So this is going actually to 3 different steps that I'm going to walk you. It's got loading the imagery, or I would say live video feed, run the model on the top that I show you guys later what it is, then process and actually consume this with GeoEvent, which we kind of integrated with deep learning, and then do historical analysis on top of the data that you actually save in GeoEvent, and you can pull it out from feature services. On top of that, we also visualize in a way that use dashboard. Basically, they can use in Department of Transportation to see what's happening at different intersections. So this is, I think if I can run it. This is basically example running yellow. I think I run it for Vietnam. That basically shows every single activity that happened at intersection. From motorbike, people, cars, trucks, buses, everything. We had kind of 6 classes to track them. And what it does is actually get the video, it just converted to multiple series of image, then run the model on top and get the bounding box. And then we are storing actually those bounding box in our services. And the next one, so the model that we use, is called yellow. It's called you only look once, not twice. So, okay. So we get the actually original model that trained for this application with Coco dataset. It's kind of 100 classes, I think. Then we did transfer learning. So because our imagery was different than original image that it trained for, we need to do this kind of transfer learning or do tuning. So we get like close to 1,000 imagery. We labeled them for daytime and nighttime. And this model is pretty fast. It's just you can run actually close to 6 imagery per second on GPU on AWS. And in terms of accuracy, it's super amazing. It's over 90% accuracy to detect everything, both daytime and nighttime. So here's the one for nighttime. What's only misses is this one at the end that is, I'm going to have a hard time to see with eyes. Here is the daytime. It basically captures everything. And those probability actually on the top of the box is the probability that object exists inside the box. And here is another one for daytime. You can see it even detects this car in the horizon. It's kind of even hard to see. You cannot even label it with eyes. And here is another one. So here I'm trying to walk you through, okay, we get the live feed, right? We run the model. We are just trying to store the data from like the object that we see in 110 cameras that we have. So first of all, you have to define the event. What is event? For us, the event that we had was like GeoJSON that we actually passed. We had camera ID, camera name, location, which is latitude and longitude, date time, which I guess I kind of like run this close to 2 a.m. last night. It shows the number of the car at nighttime, you know, buses, people, and everything. We also store the image, basically, that what happened at each intersection. So if you think about it, you know, for 20 hours a day, you know, we have like 3,600 seconds, 111 camera is close to 10 million records, basically. Just imagine if you want to run it live on AWS, how many records you are going to have in a month or a year. It's, you know, it's this huge data set that's actually flow to GeoEvent. So I'm going to walk you through GeoEvent to kind of, you guys get an idea that how we actually consume GeoEvent. So first of all, you need to define a schema. A schema is basically very similar to database, right? Before you write to the database, you need to define what is a schema. So here, you know, I defined the schema that's kind of actually contain each of those info that I want to store in GeoEvent, which is, you know, camera name, camera ID, and other stuff that I show, like, you know, the URL for the image and everything. And the URL for the image is actually, we have an AWS S3 bucket is actually dumped it there. So we can pull it out at any time that we want. And, you know, we have like number of like cars and everything, and you can define the type here that basically shows the type of object that you are trying to store in. So from here, then you define your input, basically. The input, you know, you define is basically you give it the name over here. Then based on the name that you give, it defines the endpoint that you are trying to write. So after we detect those objects, we actually do post-operation on REST endpoint to actually transfer it to the GeoEvent. Then you define like the JSON, you know, date, everything, latitude and longitude, because we want to monitor them and map them. Then from there, you know, you have to define the time set. Then it goes to output, basically. For output, you know, we define actually feature class that we are writing on ArcGIS Online. And here, you know, you can select your feature class that you have. If it doesn't exist, you can give it a name. And you actually associate that schema that you find to here to write to GeoEvent. So if your schema is different than here, then you cannot write it in GeoEvent. This is just a way that GeoEvent understands it. Then I guess I'm going just to go to feature class, open it up, and show you that it's actually start to write here. So here is right now empty, right? We need to run the model, and after we run the model, it's going to show actually on GeoEvent and track like how many objects we are writing every second per frame. Then after that, we can go back to GeoEvent and see those feature class to see that you can see actually those populated over there. So this is actually so we have two types of services. One of them is storing for historical data, and another one is showing the current, what's happening right now at intersection. So the current one is only capturing the right now, and it doesn't store anything. But historical one actually store everything in the back. So if somebody wants to do any analysis, can always go back. And here is the service that we defined, very simple service. You have input and output, just connect them, get the GeoJSON, and put it in feature class. And yeah, the service is very similar to current data set as well as historical, except for historical, you are writing actually more data set, as I show. So here just showing the services. Then I guess it's this one over. So here is actually the fun part that we push our code on AWS. We had enterprise in AWS. Everything is actually running on AWS. So if I run it, you can basically see this is the code that is running, sending those GeoEvent, GeoJSON, and you can see that it's writing on GeoEvent right now. So I guess we are writing close to 10 feature per second. You can think of 10 camera actually. We had this originally was running to like 60 or 70 seconds, right? Then we push it down to 5 seconds right now. We are so close to actually live time that's happening. So here I'm going back to feature class, then you can see that the feature class was empty. It started to populate with those data. With those data, we have ID, number of the car, and here is actually the URL for the image. You can actually click it. It's going to go to S3 bucket. It's going to pull it out for you. If you have the hyperlink, you can put it here, get the image. And I guess this is for 5 a.m. Yeah, 5 a.m. DC time. It was like 2 a.m. here in Redland. And so the other one, I think, yeah, so you can basically see if you update it, you can actually see the number of features change. It's start to adding rows. So you can basically think like a shotgun that is like shoot data to GeoEvent, and GeoEvent consume it and put it here. So here again, it shows the model. And so I'm gonna go to dashboard and pass it to Dan. So this is what, I did video last night, but we just want to try it live too, to see how it's gonna turn out.
Yeah, you guys know how live demos work. We weren't sure if it was going to be running for the demo, so we wanted to show you the video and make sure it was working. But this is actually running live in DC right now. So we're processing 110 cameras or 111 cameras. It takes about 10 seconds to go through all of them. This is on one machine with one GPU. This can be scaled up to many GPUs, many machines, that we can process hundreds, thousands of cameras in real time. So this is an overview of Washington, D.C., but if we actually zoom in on the dashboard to more local areas, you can see extra symbology pop up that now is showing the number of cars, the number of bicycles, the number of motorcycles, and the number of pedestrians. If I select one of these points, I can see the latest image from that location. So I detected 3 pedestrians, and I'm actually, with my eyes, struggling to see all of them. There's one there, there's one there.
12 cars.
But you can see we're definitely getting most, if not all of them. There's certain circumstances where the camera quality is pretty bad, so it doesn't get everything, but overall it does a pretty good job. So that's it running live. So
then, let's say we got the data, right? What is next? How we are going to use this data set? That dashboard actually was showing what's going to happen in different intersections, and they can track activity and see where are more crowded compared to others. Other thing that we are thinking to incorporate is actually anomaly detection, seeing, using historical data, let's say run it for 1 week, and aggregate the data at like the number of objects per hour, and after that, if you keep those historical data, you can see if like somewhere like event happened at intersection, it get crowded, we can actually put the flag in the camera and say, something is suspicious happening at that intersection, go check it out. It's like basically like a flag things that goes to them. And second thing that we did basically was another type of anomaly detection, finding pedestrian in unsafe location. And there are like, so many ways of doing it, but instead of like extracting crosswalk from imagery, which were not really that great, on top of that this crosswalk changed from camera to camera, we decided to go another way. Basically, I run the model for a few hours, and those dots actually show where people walk in that intersection in rush hour. And from those dots, you can basically see that those dots can actually build crosswalk as well as sidewalk, so you can actually see where it's happening. Having that, you can run anomaly detection on the top and can detect this person that's actually walking somewhere rather than crosswalk, going from one side to another side. And this is just a start. I guess we are just planning to do much more stuff after like storing enough data set, but this can be easily integrated with any other location. We are working with other customer in another state to kind of like convert it to the solution easy that we can easily, incorporate it with other states. Easy? I said easy too much. But I guess the last one is you guys, we appreciate if you guys can fill out the survey and tell us how we did so we can make it better for UC Esri. Any question?